let's welcome our first speaker of the day. So our first talk is from Jos Oomens from Felix, who's going to be telling us about infrared spectroscopy of protonated fullerenes.
Yes, in Nijmegen in the Netherlands, this is what it looks like on a nice and sunny day. Yeah, so I just came back from giving a lecture here at the working group meeting of the Nanospace Consortium. It was a great pleasure to be invited here, and I'd like to share sort of the contents of my lecture with you. This whole story sort of started with a paper by Harry Kroto that we read, and then, Harry Kroto, of course, known as the discoverer of C60, but he was also an astronomer and a spectroscopist. And long before it was confirmed that C60, so the soccer ball-shaped molecule, was actually present in space, he was already convinced that it was there, and he was also, already thinking many steps ahead, and he was thinking not only C60 is there, but there must also be many derivatives of C60. And so one of the major derivatives that he suggested was then protonated C60, so C60 with one proton attached, C60H+. And so we were actually surprised that there was in the whole literature, this is a suggestion made by Harry Kroto in the early 90s, and it's now 30 years later, that we did not find any spectra of C60H+ recorded in the laboratory or even calculated. And so we, as we are ion spectroscopists, we take spectra of ions, we sort of figured, this be a good target. And so we mounted this new source called the DIP source or the APCI source onto our mass spec, and that actually proved to produce C60H+ very abundantly and very stably and very nicely. And so then we could combine that with our free electron laser, the infrared free electron laser Felix, that's able to scan over the whole infrared wavelength part and so record this spectrum finally. And that was the first spectrum of C60H+. And there are many interesting aspects to that spectra, both astronomical and also from just a molecular physics perspective. And to start with the last one, if you put one proton on C60 being this super symmetric cage molecule, and if you attach that one proton, you sort of break all the symmetry that's in that molecule, and that has huge consequences for the spectrum. Any spectroscopist knows that the selection rules in a spectrum, infrared spectrum or other spectrum, are determined by the symmetry of the molecule. So going from a molecule C60 with super high symmetry to C60H+, which sort of seems like a minor change of the molecule, it's a huge change in the symmetry of the molecule. It breaks all the symmetry that the original molecule has, and so it changes all the selection rules. And so for the spectrum of C60, which is very empty, almost all the transitions are not allowed, are forbidden because of the strict symmetry rules. That's all lifted if you attach that one proton, break all the symmetry, and now all the bands suddenly are allowed and light up in the spectrum. And so the spectrum of C60H+ turns out to be very different from the spectrum of C60. And that's really, I find it really a textbook example of, the influence of molecular symmetry on spectroscopy. And so that's why I like this study so much. And then, from an astronomical point, it turns out that the spectrum that we recorded, we then, I'm not an astronomer, so I can only put two spectra on top of each other and see if they're similar or not. And so we selected some astronomical, so observational spectra that were recorded for objects, so interstellar clouds or circumstellar clouds, that were known to be high in abundance of neutral C60. So neutral C60 has these four very particular bands, and they were very well visible in those spectra. And so we took the spectra of those objects, overlaid it onto our new laboratory spectra of C60H+, and you see that there is actually some structure in the astronomical spectra that matches quite well onto the spectrum of C60H+. It's not a one-to-one match, and it doesn't explain everything, but I think these are features that are sort of due to fullerenes in general that have no symmetry, that somehow have their symmetry broken such that all these bands light up. And so we recorded also spectra for a few other derivatives, of course C70H+, but also C60 with an oxygen atom on it. and their spectra are all sort of similar in the sense that they have bands in the same range, and then all sort of falls in the same range as where you see these extra features in the astronomical spectra. And so this is far from a claim that we can identify these molecules now. Definitely, we certainly need to do more research, but I think this is certainly a good indication that, you know, going back to the original paper of Harry Kroto, that some of these derivatives of C60 must also be present in space. This is maybe the first indication that that's indeed the case. And so that's sort of the two aspects that I like so much about this study. And protonated, it becomes a hydroxyl group, and it's no longer an